Hello everyone. Am I audible, guys? Hello. Hello. Am I audible, guys? Okay, so today we'll be discussing Leetcode Weekly 465. I'm Suvrat Mehta. So let's start with the discussion. So the question one, restore finishing order. You are given an integer array order of length n and an integer array friends. Order contains every integer from 1 to n exactly once, representing the IDs of the participants of a race in the finishing order. And friends contain IDs of your friends in the race sorted in strictly increasing order. Each ID in friends guaranteed to appear in the order array. Return an array containing your friend's ID in the finishing order. So basically, you are given two arrays order which contains the finishing order. Let's take an example 3, 1, 2, 4, 5. 2, 4, 5. And you're given another array friends which basically contains your friends 1 2 3 1 3 4, and you need to return an array answer which contains the elements of the array friend in the order in which they appear in the order in which they appear in this array. So basically 3 appears the first, and then 1, and then 4. So basically answer array would be 3, then 1, then 4. So to solve this problem, what we can do is we can basically, since we are also given there are people from 1 to n, right? N is less than equal to 100. So what we can do is we can create another array f, basically 1 2 3 4 5 in this case, of size n, which basically tells us if the ith number is our friend or not. So basically it will have 1 1 1 and 0 0. So if f of I is equal to 1, then I is friend. Else not. So basically if we create this array, it will help in finding the answer. Then what we can do is we can iterate in order. We can iterate on the elements of order, and if f of I, then answer dot pushback I, and after this we can return answer. So basically what is this doing? We'll iterate over the elements of order. The first element is 3. We see that is 3 1 in the f array. So yes, 3 is 1. So answer array would have 3. Then the next element is 1. We see that does f array has 1. So yes. Then the next element is 2. And then since f array has 0 for 2, we skip this. Then the next element is 4. Now since f array has 1 for 4, so we take that. Then 5 is skipped, so answer is 314. Now we need to create the f array, and how can we do that? We can initially make an f array with n plus 1 size and all elements are 0. And then what we can do for I in friends, f of I equal to 1. So this will create the friends array, f array. So f array is created in O of n, and this for loop also takes O of n. So overall time complexity is O of n. I'll show you guys the code. So basically this is f array and this is the answer array. For f array, I am iterating over the friends array and I am marking all the friends as true in the f array. And then for answer, I am iterating over order, and then if order is true in f of array, then I push back it in answer and return answer. So this was the solution for question 1. If anyone has any doubts, they can ask. Yes, you can use unordered map or map to do the same. Okay, so let's move on to the next question. So the next question is balanced k or decomposition. Given two integers n and k, split the number n into exactly k numbers, into exactly k positive numbers such that the product of these integers is equal to n. Return any one split in which the maximum difference between any two numbers is minimized. You may return the result in any order. So problem B. Basically, you are given two integers n and k, and what you need to do is find an array d1 into d2 till dk. Find an array d1, d2, d3, dk such that d1 into d2 till dk is equal to k, and the maximum of dj minus di is minimized. J comma I belongs to 1 to k. So basically, maximum of dj minus di is minimized. So that simply means that max of d minus min of d is minimized. So basically, since d1 into d3 into d till dk is equal to k, then d1, d2, d3, and dk are all divisors of k, right? So basically, in the array, we just need to minimize the difference between maximum and minimum element. So minimize the difference. We need to minimize the difference between maximum and minimum element. And let's see the constraints. Constraints are n is given till 1e5 and k is given till 5. K is from 2 to 5. So basically, since k is from 2 to 5, we can try and force for the answer. So first let's check if we can brute force or we can't. So basically, let's say that n is equal to let's do prime factorization of n. So it must, after prime factorization, it must look like this: p1 into a1 into p2 into a2 till pk into ak. P actually not k, let's take px into ax. So basically, we can also write it like this: p1 into p1 a times into p2 into p2 a2 times, and then px into ax, px into px ax times. So basically, since d1 into dk is equal to n, right, and these prime numbers cannot be further multiplication of other numbers. So these has to be in one of the these numbers. So basically, the total number of possible combinations of D1, D2, 3 till dk would be simply dividing all these in k groups. So basically, P comma P2, P comma P1 comma P1 A1 times, P2 comma P2 comma A2 times, Px Ax times. So basically, divide this in k group. So if when we divide these in k groups, the multiplication of all the k groups will give us n, right? So what are the total number here? A1 plus A2 till Ax. So we need to distribute these many things in k groups, right? And A1 plus A2 till Ax would be less than equal to log n, right? Because basically they cannot be more than log n, since the smallest value, since we need to maximize A1 plus A2 plus till Ax, what we can do is we can take the smallest value of P. So the smallest value of P would be 2. So n equal to, let's just say, 2 into 2 to the power A1 plus A2 till Ax, right? So now A1 plus A2 till Ax would be less than equal to log n base 2. So simply this. So A1 plus A2 till Ax would be less than equal to log n. And now we need to divide this in k groups. So what we can do is let this number be some p actually. Now we have p things to divide in k groups. How we can do this? Basically, let's say that I have p items on the ground like this. So this is item number 1, 2, 3, 4 till p. And now we need to divide it in k groups, right? So what we can do is we can place some barriers like this, and each barrier we place, it divides into two groups. So basically, if we place k minus 1 barriers, it will divide in k groups. So like this, we can place k minus 1 barriers. Basically, let's take an example for 5 things, 1, 2, 3, 4, 5. If we need to separate in 3 groups, what we can do is we can place 2 barriers. So we'll have now 3 groups. And the number of places that we can place these barriers would equal to p. And we can choose k places out of these. So k minus 1 actually. So approximately this. Actually, to find the exact number, we can only place the barriers towards the right of every element, and we cannot place towards the right of this element. So p minus 1 c k minus 1 would give us number of ways to distribute in k groups. Where each group is not empty, where each group is non-empty. So approximately PCK, but in our case, the group can be empty, because empty group would just mean that di is equal to 1. So we can say that approximately p minus 1 c k minus 1 would be the would be the total number of different combinations. Exact would be, I think, p minus 1 c k minus 1 plus p minus 1 c k minus 2 till p minus 1 c 0, because this will give us for k groups, k minus 1 groups, until 0, just one group. So basically, for the case when there are k minus 1 groups, we can just add one single plus 1, so that will make it k groups. So yeah, approximately there would be, let's say, PCK different groups, and PCK would be a small number since P is log n and K is maximum 5, and log n of 10 to the power 5 would be approximately 5 into 3, let's say 16 17, it would be something. And 16 17 C5 is not a very big number, because let's do the math. 16 factorial upon 11 factorial into 5 factorial, so 12 13 14 15 16 upon 5 4 3 2. So 4 into 3 12, 5 3, this 7. So this is not a very big number. So we have a small number of total possible different distributions. So we can brute force. This was the proof that we can brute force. Now let's see how we'll write the brute force. So basically, let's define a recursion. Brute of n comma k comma, since we don't need permutations, basically different permutations would give us same answer, right? So calculating all the different permutations would be just waste of complexity. So just let's have another state in our brute force as last, and then a vector of curve. So basically, from this brute, we can go to next state of n by d comma k minus 1 comma d comma cur dot pb d. So basically this would be, and to terminate our brute force, when k is equal to 0, we can simply we'll get our current, whatever the current has, answer equal to current if current of basically max in current minus min in current is let's say less than whatever value we had previously. So then answer would be, if this, then answer would be cur, and val would be max minus min. So how exact, why this brute force? And also d is divisor of n. So basically we need to iterate over all divisors of n to brute force, and d must be greater than last, because if we don't apply this condition, then what will happen is, let me take an example. Let's try to brute force for n equal to let's say 4 and k equal to 2. So first of all, we know that it would be 1 comma 4 and 2 comma 2. These can be the only two cases, right? So let's try to see what our brute will do. Brute 4, so initially we'll call it brute 4 2, and let's just skip this last for now and see what happens. And initially car would be empty array. So what will happen, since 4 has divisors 1 comma 2 comma 4, right? So for each d we will have to call a recursion. So brute 4 by 1 comma 1, and then cur will have 1. Another brute 4 by 2 1, cur will have 2. And the last brute 4 by 4 1, cur will have 4. And now for the, also we can add another condition in the brute force. If k equal to 1, we need to only take one d which is equal to n, because any other d would not give us n equal to 1 in the end. So that current vector would not multiply to n. So basically from this we will have brute 1 comma 0 comma cur 1 comma 4. From this we will have root 1 comma 0 comma cur 2 comma 2, and from this we will have root 1 comma 0 comma cur 4 comma 4. So 4 comma 1. So basically these would be the base cases that we arrive in the end. So we can see that we are having three possible groups: 1 4, 2 2, and 4 1. So checking for this 4 1 is not required. This would be just a waste of time complexity, and also we did not prove for all the permutations that the number of permutations would be small. We only prove for combinations. So we only know that the number of combinations would be small, so we need to purge out these permutations. So to purge out these permutations, what we can do is we can have another variable, this last. So what will this do? Now let's try to again run the brute force with this last variable as well. So brute 4 2, initially the last would be set to 0 and current it would be empty. So what this will have a transition to brute 4 by 1 comma 1 comma last now would be 1 comma current would be 1, and another one would be brute 4 by 2 comma 1 comma 2 comma current is equal to 2, and another would be brute 4 by 4 1 4 current is equal to 2 4. So now this will give us the transition brute 1 comma 0 comma 4 comma cur is 4, 1 comma 4, and this will give us the transition brute 1 comma 0 comma 2 comma cur is equal to 2 comma 2, and this will not be able to give us any transition because the last value was 4 and currently we can only take 1, and since 1 is less than 4, so this transition would not be possible. So we are doing transition only if d is greater than equal to last. We are only doing transitions when this. So this would be terminated here, and we would have only these two base cases which would be perfect for us. So doing this brute will help us get the answer. So I'll show you guys the code. So basically also we need the divisors while doing the brute, right? So to get the divisors I have run, okay, let me just explain that as well. So we would need the divisors as well, right? So one thing we know that if we calculate all divisors of n, so then any divisor of n would have a divisor from that only, right? So basically we can just calculate all the divisors of n, and those would be the and we can just use those divisors for all the divisors of n. So what we can do is for I equal to 1 to I into I less than n and I plus plus. So if n percentage I is 0, then divisor dot pushback I and divisor dot pushback n by I. Also we need to separately handle, we can just add another if statement here. If n by I not equal to I, divisor dot pushback n by I. Basically if n by I is equal to I, we would just simply be pushing back to same values. So we can calculate number of divisors like this in square root n complexity. So basically we'll pre-calculate all the divisors before running the brute. So let me show you guys the code now. So basically here I am pre-calculating all the divisors, and this you can replace this with that if condition if you want, but it is essentially the same. And then I am sorting all the divisors, and then now I am conducting my brute. So basically, initially I call brute with n, k, 0 and cur. 0 is the last, k is the number of elements that I have to take, n is the current value. So we'll come at the base case later. So basically what I do is find an index ind. Ind is basically nothing but lower bound of last in the array div. So div is the divisors, right? And since we need to take the divisors greater than the last divisor that we took, so what we can do is we can take the lower bound of last in div array. Now this will tell us, this will give us the exact index that will have the value greater than last. So we will only need to iterate from that index till the end of div. And now, so the current d would be div of I. And if n percentage d is not equal to 0, that means that d is not a divisor of the current n. So we'll just continue. Else, if it is a divisor of the current n, we can push back in cur, and then we can call the brute with n by d, k minus 1. Basically, n by d would be the new number, k minus 1 would be, now we need to choose only k minus 1 k minus 1 divisors, and d would be the last divisor that we use, and current will hold the uh, total array. So, and after this brute, we can just again pop back the d that we pushed in current. Now, if k is equal to 1, that means we are now taking the last element of the divisor array. So if so the last element must be equal to the current n, right? Because if it is not equal to the current n, then the total multiplication would be not equal to n. So last element must be equal to current n. So if current n is less than last, so that means last element is not possible to take. It must be coming in some other permutation already. So we can return this. And if n is greater than last, then we can simply push back n to current and then brute. So 1, 0 divisors now left, and the last element was taken as n and current, and then we can pop back current. Now to calculate the answer, when k is equal to 0, we will have a possible value of this curve variable. So we can just take it into another temp variable, and since we were using this last variable, so we don't need to sort this array, it will already be sorted. So we can just do last value minus first value. Now if this last value minus first value is less than equal to val, then we set val as this and answer as this. So this will finally give us the best possible answer, and then we can return that. um okay, so after finding divisors, how I make maximum difference minimum, it is unclear. Okay, I'll explain again, just a second. Hey, but lower bound is greater than equal to last. So yes, we are allowed to take greater than equal to last elements. Basically, I wrote that here somewhere. D is greater than equal to last. Basically, because the divisors can be same, right? It does not need to be strictly increasing. It just need to be increasing. Sir, I couldn't understand the second solution. We are dividing the factors in k groups, but what if there is a partition in which a later coming divisor is in multiplied to some smaller divisor? Um, or- and yes, yes. Basically, okay. We are not. What this was doing was simply we have p different things, p things and we need to divide it in k groups. This was doing that, and this can be anything. This can be either p1 or p2 or p3 or pk. This can be anything. This can be, this does this is not in increasing order. It could be anything. Basically, this is not a very exact bound, but we just found out this bound to know whether our brute will work or not. So basically, in our brute, what we are doing is we are trying to distribute in any order. Basically, we are iterating over the d, right? So all the orders would come, all different permutations, all different combinations would be. And how we are maintaining it in code, I thought of a bit mask approach with but and with TLE. Bit mask approach, there will be a law. Okay, you can do that, I think, but Leetcode generally has a very strict time limit, and when you are doing bit mask approach, what will happen is basically you will end up recounting the combinations. Let's say that for 6 you have for 6, let's say n equal to 6 and k equal to 2. So you will have 1 6 2 3 3 2 6 1. You will count all these if you maintain a bit mask, because initially your bit mask will have 0 0, right? And then you will either take this, basically using bit mask you will recount all the permutations. And if we don't use bit mask and if we maintain this last value, so that would ensure that the arrays that we are generating would be in sorted order. So if they are in sorted, we would not be recounting different permutations. Also in bitmask as well, you can change your solution a little bit and add that last state as well. So that will eliminate a lot of different permutations. So what if we brute force the values, like generate all combinations for k as max number of divisors or factors for 1.5 is 36. So factors for 1.5 is 36. 36C5. Uh, 36C5. Also some number lesser than 1E5. Okay, max number of factors for n equal to 1 number of 5. Some number less than 1E5 might have more number of factors, and basically if you are brute forcing, then you will have number of divisors to the power 5, maximum complexity, since you will need 5 for loops to brute force over all the 5 values of number. So number of divisors to the power 5, and number of divisors are of generally the complexity cube root of n. So n to the power 5 by 3, and n is 1e5, so 10 to the power 25 by 3. So this will be greater than 10 to the power 8. So this would give you TLE. Actually 36C5 will not work, because we can take the same divisor twice. For example, for 4, 2, 2 is also a valid combination for 4 and k equal to 2. But if we do for 2 comma 2, 1 comma 4 are valid permutations, right? But this 2 comma 2 is not counted in 36C5 because, okay. How does binary search is applied for finding the index in the brute function? Basically, so we have this div array which contains all the divisors, right? So we need to choose one of these divisors to move on to the next state of our brute. So since the last divisor that we took was last, and we need to take a divisor greater than this, so we'll apply lower bound to find the first element greater than equal to last, and from there we can choose any divisor. So that's why we can use lower bound to calculate the index. Even if we don't do this, we can apply a condition here. If D is less than last, then we can continue. But this will be a little more time costing, because now we will have to check for all the divisors 0 to div dot size. So a little bit more computation, but I think this will also pass. Okay, so let's move on to the next question. So maximum product of two integers with no common bits. So you are given an integer array nums. Your task is to find two distinct indices I and j such that the product nums I into nums j is maximized, and the binary representations of nums I and nums j do not share any common set bits. Return the maximum possible product of such a pair. If no such pair exists, return 0. So basically in this question, we need to find the maximum value of problem C. We need to find the maximum value of nums I into nums j, where nums I and nums j do not have any set bits in common. So basically nums I and nums j don't have any common set bits. Let's start. Let's take example. Let's take the test case. So it's 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. So the bit representation of 1 would be 0 0 1. For 2 it would be 0 1 0. For 3 it would be 0 1 1, 1 0 0, 1 0 1, and 1 1 0, and 1 1 1. So we can multiply two numbers which don't have any common set bit. So let's try to find for each I the largest j. Let's find for each I the largest possible value of nums j, because since now we have fixed nums I, then the maximum value we can get from nums I into nums j, we can try to maximize the nums j. So let's find for each I the largest possible value of nums j. So let's take 0 0 1. So we can have this as nums j, we can have this, and we can have this. So we'll take the largest. So for 1, the best pair is 6. Let's check for 2. For 2, we can have this and this, and also 1. So for 2, the best we have is 5. Now let's see for 3. For 3, the best we have is 4. Yes, for 3, the best we have is 4. And then again for 5, For 5, the best we have is 2, and for 6, the best we have is 1. 5, 2, 6, 1. And for 7, not possible. So since we need to find the maximum of all of these would be the answer. So this would be 1 into 6, 6, 10, 12, 10, 6. So 12 is the answer, right? So now let's try to figure out exactly what is going on. So since num_i and num_j don't have any common set bits, right? So the AND of nums_i and nums_j would be 0. Since they don't have any common set bits, this would be 0. So now basically what we can do is we know that they don't have any common set bits. So let's say that if nums was this 0, 0, 1, 0, 0. So if nums was this, then nums_j can have any of these bits as 1. Nums_j must be a submask of this. So if nums_j is a submask of this, what does submask mean? Submask means basically all the zeros have to be there, but you can set any one as 0. So basically for this, this can be a valid submask, or this can be a valid submask. So any number which is a subset of these ones, only these bits must be set. So num_j must be a submask of this, and now we need to find the maximum value of nums_j. So this is a very common problem. What we can do is we can use dp. So dp of a mask will store the maximum submask of this mask of this present in the array, present in nums array. So how can we calculate this dp? Basically, let's say that we are finding for this. So we are finding, let's just take some shorter one actually, 1 0 0 1 1 0 1 1 0 1 1 1 0 1. So let's say we are calculating our dp for this. So what will this be? This would be a maximum of dp of 0 0 1 1 0 1, dp of 0 1 0 1 0 1, dp of 0 1 1 0 0 1, and dp of 0 0 0 0 0 0 1 1 1 0 1. And so basically how did I do? Basically what is this? This is for each index in dp I am setting, if it is 1 I am setting it to 0 and keeping the rest same. So 0 1 1 1 0 1. So once I'll set this to 0, which is 0 0 1 1 0 1, and then I'll set this to 0 0 1 0 1 0 1. I'll set this to 0 0 1 1 0 0 1, and in the end I set this to 0. Okay, 0. So so any subset of this, submask of this would be a submask of one of these. How so? Basically, for a number to be a submask, either it can be same, or either it will have at least one, it will have one bit unset. basically it will have at least one bit where it was 1 originally, it would have 0. So any submask of this would be a submask of one of these. So because it must have at least one single bit that was unset. So if this bit was unset, then it would be a submask of this. If this bit was unset, then it would be a submask of this. If this was unset, then it would be a submask of this. If this was unset, then it would be a submask of this. If a pair, if let's say these two bits were unset, if let's say these two bits were, if let's say these two bits were unset, then it would be a submask of both of these. It would be a submask of this and it would be a submask of this. But since we are just taking the max, it wouldn't matter if the numbers are repeating in two states, because we just need the max. If let's say these 3 bits were unset, so it would be a submask of these 3 states. So we have got this transition, which is basically for each. So we have got this transition, and initially what we can do is dp of num we can set as num I. So initially we can do this. Let me just write the transition how we'll do. For each bit 0 till bit whatever max bits we have, and bit plus plus. And for each mask, since for a current mask we need to know the value of the lower masks, so we'll have to calculate from 0 to max mask, mask plus plus. And the transition would be if mask has the bth bit as 1, so bth bit as 1, then what we can do is answer equal to max of answer comma mask, and we can unset the bth bit. We can simply XOR by 1 left shifted by b. So this dp of, this is not actually answer, let me just, dp of mask would be equal to maximum of dp of mask comma dp of mask XOR 1 left shifted by b. So basically this will unset the bth bit, and initially I can put these values inside the dp, because apart from these cases, if this number is present in the nums array, then that would be the highest submask present, because any number greater than that cannot be a submask of this. This is already the greatest number that can be a submask of itself. So the number itself is the greatest submask. So if the number itself is present in the nums array, then we set dp of num I as num I, and then we can use these for loops to calculate the other states. And now after this dp, we basically know for each mask what is the maximum submask. So for I in nums, j would just be equal to dp of nums XOR 1 1 1 1 1 1 1 1 1. So basically XORing it with 1 1 1 1 1 would just be would just do this. If we had this as I, then it will give this. This would be j I, and this would be j, because we are just inverting each bit, and XORing with 1 inverts each bit. So we can just take XOR with 1 1 1 1 1, and whatever is the highest submask of this would be j, and we can just take maximum of all I into j. So we are calculating this dp in O of maximum bits, which will 20 into 2 to the power 20. So this would be around 2 into 10 to the power 7. and this is O of n. So overall time complexity would be O of 2 to the power x log 2 to the power 20 log 20. I'll show you guys the code. Basically, MSB is the number of bits, so it would be log the maximum number of in nums, and maximum mask would be 11111. Each bit to be set at 1. So what we can do is 1 to the power MSB plus 1 minus 1. So basically 1000000 minus 1 would give us 11111. So we are doing that. And then we are calculating this dp, where initially we will set dp of x as x, and then we can calculate by this logic for all other masks, and the answer would be on 1 n into masks or n. New max mask is just 11111. So this was the solution for problem C. Why not for question 2 simply create all 2 to the power log n subsets with repetition such that net product of element equal to n using recursion, then simply iterate over. We are exactly doing that. We are literally creating all the subsets such that the product of elements equal to n with repetition. We are doing exactly that. This is always possible, right? That nums I or nums j will be nums I plus nums j. Yes. Since nums I and nums j don't have any common bits, so nums I or nums j will be nums I plus nums j. Why does nums I and nums j equal to 0? Max of nums I into nums j, answer condition cannot work after. If you do it like this, won't you require 2 for loops for checking over all pairs? So that would be exceeding the time limit. What would be the rating of C? I think 1800. I think 1700, 1800. On what topic and pattern question C is based on? DP and max, I think. How log 2 max element is a trick, right? And find set bits. It is a trick, right? Log 2 max is basically, let's say I have an array with elements 1, 2, 3, 4, and 5. So I need to know how many bits do I require to solve this array, right? So I need to know the maximum number of bits in any element. So the maximum number of bits would be in the highest element, and taking log 2 simply gives the maximum number of bits. So when I take log 2 of 5, I'll get something 2 point something. So that means the maximum number of bits would be 3. So I'm doing that just to find the maximum number of bits present in any number. I solved third using logic similar to take you forward maximized OR problem. Basically, you can move from the highest bit to lowest bit, and in the try you can check if the current bit, if there is any number, if the current bit is 0, you can check in the try if there is any number with the current bit having 1 and move forward and see if there is a number. Yes, you can do that as well. So let's move on to the next question. Sum of beautiful subsequences. So you are given an integer array nums of length n. For every positive integer g, we define the beauty of g as the product of g and the number of strictly increasing subsequence of nums whose greatest common divisor GCD is exactly g. So return the sum of beauty values for all positive integers g. Since the answer could be very large, return it modulo 10 to the power 9 plus 7. So problem D. Basically, we are given an integer array nums, and what we need to do is we need to calculate g into count of all strictly increasing subsequence whose GCD is g. Count of all strictly increasing subsequence whose GCD is g. So basically we need to do this for, and g can be anything. It can be anything. So how this? Let's just try simply. First of all, let's just try for a given g. For a given g, let's try to count all the strictly subsequences whose GCD is g. So find all strictly increasing subsequence whose GCD is g. So first of all, what we can do is basically for a given, since we have fixed the g, right? So now in the subsequence, we can only have elements which are a multiple of g, right? So let's say if I had some array like 1, 3, 2, 5, 7, 8, 12, and if I am fixing the GCD to be 2, then all these elements do not matter to me. Only answer would be found only using these elements. So for g equal to 2, I only need the array 2, 8, 12. So let's first get rid of these numbers and try to focus on solving the problem using this array. So now the next what we can do is since we need to now find the, this array is kind of a bad example. So let's just take some other array like 4, 2, 12, 18, and 16. So let's just take this example. Let's say that there was some array, and for g equal to 2, these were the numbers that were divisible by 2 in the array in this order. So now basically need to find the strictly increasing subsequence number of SIS in this with GCD with GCD equal to 2. So yes. So basically another step that we can take is we can divide all the numbers by g. So that would give us the array 2, 1, 6, 9, and 8. And now our problem has changed to number of SIS in this with GCD equal to 1. Because basically if GCD of GA1, GA2 till GAK AN was equal to G, then GCD of A1, A2 till AN would be equal to 1. So simply we have divided all the elements by G, and Now number of SIS in this with GCD equal to 1 we need to calculate. So how can I do that? How can we do that? Let's just now again we try to break this problem in two different parts. What we can do is, let's just for now focus on calculating the number of SIS in this. Number of SIS in this. Let's first try to find out the number of SIS in this. So how can we calculate the number of SIS in this? Let's try to first solve it really simply. Let's create an array with 1 2 3 4 5 elements, and let's denote them as this array in sorted order. So 1 2 6 8 9, and this array will have indexes 0 1 2 3 and 4. This array is currently empty. All the elements are set to 0. These values these values are just for reference. They basically just correspond to the index. These are the index, and these are the values in the current array. And what this array tells us is the number of SIS ending at basically this number. This index will hold the value of number of SIS ending at 6. This number will hold the value of number of SIS ending at 8. Okay. So initially all values are 0. Now let's try to process this array. So first element is 2. And since this is the first element, we don't really have any other SIS ending at 2 or any other number. So what we can do is, we now have an SIS ending at 2. We have this SIS. Now the next number is 1. So we have another SIS which is ending at 1. Now the next number is 6. So we have another SIS which is ending at 6. And both of these SIS can also be extended with 6. So 2, 6 and 1, 6. So what can we do is, sum of 1 plus 1, 2, and then another 1. So 1 plus 1, which is the sum, and another 1, so which is 3. Now the next element is 9. So again for 9, we can extend all these SIS 9. So the value for 9 would be 3 plus 4 plus 1, 5, and another 1 for just simply 9, so 6. And now ending at 8, 8 can be extended. We can extend all these by 8 again. So 3 plus 1, 4 plus 1, 5, and plus 1 for 8 alone. So this. And now since we processed 8 after calculating the answer for 9, we would obviously not make this kind of mistake where we are extending the SIS ending at 8 with 9. So we only extended the SIS ending at 1, 2, 6 and 8, and 8 was 0 when we were calculating for 9. So in this way we can calculate the SIS, number of SIS ending at each number, and then sum of all this would be the total number of SIS. So 6 plus 6 plus 3 plus 1 would be the total number of SIS, 12, 15, 16, 17. So 17 would be the total number of SIS, and in this way we can calculate the total number of SIS. Now let's analyze the time complexity. For each number that we are processing, we need to take sum of all the smaller numbers in this array. So basically when we are calculating for 9, we need to add the value at the first 4 indexes. So this was naively take O of n complexity per update and total O of n square, right? But what we can do is, we can use a data structure like Fenwick tree or segment tree, which allows us to update any element in an array and take the prefix sum of the updated array in log n time complexity, and update also in log n time complexity. So basically we can use that to convert this in O of n log n, since now we will know the prefix sum in O of log n. and we can also do the update for each step in O of log n. So we can calculate the number of SIS in an array in O of n log n, right? So now we know this. I'll explain how exactly fen victory works and how it will calculate in log n time. I'll explain that later. For now, just assume that there is a data structure that can let us update one element in an array and let us calculate the prefix sum of an array till any index. So basically, again I'll again let me just once more do a dry run on this array. That would make it more clear. So 21698, right? 21698. So we'll create our array which will have 21698. So 12689, and the indexes of this array would be 0 1 2 3 4, and first all the elements would be 0. So now we need to update, we'll start updating from here. So we have 2, we will take the prefix sum till 1, which is 0, plus 1 will come here 1. So next element is 1, we will take the prefix sum of before it, which is 0, plus 1, 1. So for 6, we'll take the prefix sum of elements before it, so 2 plus 1, 3. For 9, we'll take the prefix sum of elements before it, so 3 plus 1 plus 1, 5. So 5 plus 1, 6. For 8, we'll take the prefix sum before it, 3, 4, 5 plus 1, 6. So we got the same array 11366, and the total number of LIS would be sum of all this, which is 17, I think. Yeah. So we have found a way to calculate the total number of SIS, right? Now let's try to find. We have solved this number of SIS in this. Now we need to find GCD equal to 1, because in the current case, also we have counted these subsequences also 2,8, 6,8, and these subsequences do not have GCD equal to 1. As GCD has 2, this has GCD has 2, right? So what we can do is, let's just denote the number of SIS for a given G as count of G, right? Number of SIS for a given G. And we need to find exact of G, which is the number of SIS for G with GCD equal to 1, right? So we need to find this exact of G. Basically, the answer for this question is G into exact of G, right? So we currently have only count of G. So how can count of G to exact of G? So basically, we know that count of G in this, the GCD might be GCD equal to 1 or 2 or 3 and so on, right? So what we can do is count of G minus equal to exact of J into G, where J is greater than 1. So basically, exact of J into G will give us the exact number of SIS where GCD equal to J, right? So this will be the number of SIS where GCD is equal to J. Basically, GCD is equal to J because we only divided by G, right? Actually what this will contain is, when we divide all the numbers by J into G, then GCD equal to 1. That count will contain. So, but for this count G, this contains this value, and if we subtract all of the different GCDs apart from 1, then we will have this would be equal to exact of G, right? So now for each G, we know a way to calculate the number of SIs in O of n log n, right? And after calculating count of G, we again know a way in O of n to calculate from G exact of G, and then we can perform this to calculate the answer. And now, since GCD would be always less than equal to maximum element, right? So for G equal to 1 to maximum element, this J would be max upon 1 plus max upon 2 till max upon max, right? Because J into G would also be less than equal to max. So J would be less than equal to max upon G. So max upon 1, this loop will be iterating only this many times, and this is basically a log n complexity. So this is max into log n complexity, max log max, actually max log max complexity. So we know that this loop will only be running max log max times, and now where did that go exactly? Yes, for this, for this also will go a maximum of max log max complexity, because for each O of n size array we can calculate SIS in O of n log n, right? And for a G, the maximum size would be max upon G. For 1G, the maximum size can be, we can have all the elements G, 2G, 3G till max till some J into G. We can have all the elements in the array, and this will have a count of max upon G elements. So again, it would be max upon 1 plus max upon 2 plus max upon 3 and so on. So this will also be O of n log n complexity. And since we need to know the value of exact of greater than, basically since to calculate the value for G, we need to know the value of numbers above than numbers greater than G. So we can do the for loop from last max n to 0, from max element to 0. So basically this will ensure that we have calculated all the greater values. So we will be able to perform this. So I'll show you guys the code first, and in the end I'll explain a little about Fenwick trees. So let's currently skip the Fenwick tree. So now this function n is the size and mx is the maximum element present in the array. Now what this for loop is doing is basically for each G I am calculating what numbers are a multiple of G in the array nums. So basically what I'm doing is I'm iterating over x in nums, and for all the divisors of x I'm using that square root n loop to iterate over all the divisors of n, and for all the divisors of m I am pushing back x by, basically x is a multiple of all the divisors of x, right? And x is a multiple for all the divisors of x, and what we are doing is we have so we divided all the numbers with the GCD, right, that we needed to calculate for. So we divided all the numbers with GCD. So what we are doing is we are dividing all the x by d. So if d and d2 are the divisors of x in this iteration, so for d we are pushing back x by d, and for d2 we are pushing back x by d2. So now after this we will have for each G what are the multiples of G in nums, and we have divided all the multiples of G by G. We have already divided all the multiples of g by g. So after this, now we have to find this exact array. To find this exact array, we will for loop from the last element to 1. Basically, since we need to know the value of greater elements to find the value of smaller elements, and this will copy the current sequence in v. So if v is not empty, basically what we can do is we can copy another comp vector and we can sort that comp vector to get this array 1 2 6 8 9. We can sort that comp array to get this array, and we can create a Fenwick tree which initially has all the elements as 0, and then we can iterate over the elements of v. We are iterating over the elements of this, and for each element what we are doing is this r is the lower bound in comp array of val. So basically when we are processing 9, the lower bound of 9 is basically the index where 9 is in this array. So when we are processing till 9, we know that the index we are currently at is 4. So what we can do is we can bit.query gives nothing but sum till r minus 1th index. So since r was this index, so we are doing sum till this index, and then we are adding another one for just 9, and this would be the new value at the present index, and then this update function updates the value at this index to cur. So basically we are taking the sum of all the smaller elements and then adding 1 and updating the current element, and doing that for all v. And in the end, the count will come out to be bit.query sum of all elements. So sum till the size of comp. And now we need to subtract this exact g from this count. Now we need to perform this loop, right? So what we are doing is for g into 2 till maximum element, and we are adding g. What we are doing is we are maintaining a variable sub and adding exact of k to sub, and we are also applying mod as well. And in the end we are doing count g minus sub. That would give us the exact for g, and exact g is equal to exact, and the answer would be this this thing, g into exact of g. So answer we add exact into g percentage mod. So and then we return answer. So that was the solution for the last problem. If you guys have any doubt in this, please ask, and I'll explain the Fenwick tree after this. I'll just give the brief overview of how a Fenwick tree works. I don't really give Leetcode contest much, so I don't have a rating on Leetcode. So I don't think you guys have any problem with the solution. So I'll just explain the Fenwick tree briefly. So what Fenwick tree does is basically helps us update an index. What Fenwick tree does is basically, let's say we have an array. Fenwick tree lets us calculate the sum till at some prefix sum of this array. Basically we can do prefix sum till I using Fenwick tree. And how Fenwick tree works is, let's say that this is 1 2 3 4 5 6 7 8 9. So the seventh index of the Fenwick tree would hold the value for, since 7 has a binary representation of 1118. So we take the last set bit and put it to 0. So this will store the value for 110 plus 1 till 7. So this is storing the value for just 7 till 7. And let's take another example, bit of 6. So bit of 6 has a binary representation of 110, and we set the last set bit as 0, so that would give us 100. So bit of 6 holds the value for 100 plus 1 till 6, that is 5 till 6. Then bit of 4, let's find the value. 4 is 100 and we unset the last set bit, so this will store the value till 1 till 4. So let's say now I want to calculate the, let's say I have calculated somehow all the value of bit. I have calculated this bit array, and now I want to find the prefix sum till 7. So what will happen is, basically I'll add bit of 7 to my answer. Bit of 7 was the sum of this value. So I'll add bit of 7, and then I will add bit of 6, and then I will add bit of 4 to my answer. So since I added bit of 7, it gave me the sum from here to here. I'll move back, and now I'm on 6, and 6 gives me the sum from 5 to 6. So if when I add bit of 6, I'll get this sum, and I'll move on to here. And now when I add bit of 4, then it will have this sum. Basically we are unsetting the last set bit, so we will maximum perform this operation O of number of bits times. So in O of number of bits time, we would have moved till the first index, and we would have gotten all the sum. And to update, basically when we are let's say updating the fourth index, so we would need to update all the values, all the indexes in bit where 4 is in the range of its sum, right? So basically let's try to find which ranges have 4. So 4's binary representation is this, and to find which indexes of bit has 4 in its range, we will now, before we were subtracting the last set bit, now we would be adding the last set bit. So this plus 100 would be 1000. So we need to update the value on 8, and then again we will add the last set bit 1000. So 1000. So we will need to update the value on 16, and since we are doing this once, we will be doing this only once for each bit. So maximum O of number of bits. Let's take another example. Let's say I am changing the value at 5th index. So 5 has binary representation 101. So I'll be adding the last set bit, so it will become 110, which is 6. So I'll be adding the number at 6 as well, add bit of 6, and then again I'll add the last set bit here. So this would become 1000, and now I'll be adding the value at 8, and then 16, and so on. So this is how we will be updating the Fenwick tree. So I won't be going into very details of Fenwick tree. You guys can learn that. This is how we are doing it. So that was it for the discussion of today's contest. So thank you guys.